Imagine you have a microcontroller, the brain of your electronic project. Now you want this brain to talk to other components like sensors, memory cards, or even other microcontrollers. This is where SPI comes in. SPI stands for Serial Peripheral Interface. It's like a language that allows your microcontroller to have a conversation with these peripherals, sending and receiving data to get things done. Think of SPI as a high-speed train line for data. It's a way for your microcontroller to send information quickly and efficiently to the devices it needs to control. SPI is a synchronous protocol, meaning both the sender and receiver are synchronized to a clock signal. This ensures that data is transmitted correctly, like two dancers moving in perfect harmony. SPI is a full duplex protocol, which means data can flow in both directions simultaneously. Imagine a two-way radio communication, where both parties can talk and listen at the same time. This makes SPI very efficient for applications where data needs to be exchanged quickly and in both directions. Overall, SPI provides a simple and effective way for microcontrollers to communicate with a variety of peripheral devices. Its speed, simplicity, and versatility make it an essential tool in the world of embedded systems. In the world of SPI, there are two main players, the master and the slave. Think of the master as the conductor of an orchestra. The master decides which slave device it wants to communicate with and sets the tempo for the data transfer. The slave, like an obedient musician, listens to the master's instructions and responds accordingly. The master device is usually a microcontroller, while the slave can be a sensor, a memory chip, or even another microcontroller. The master initiates the communication and controls the flow of data. It sends commands to the slave and reads back the responses. The relationship between the master and slave is crucial in SPI communication. It ensures that data is transmitted correctly and efficiently, much like a well-conducted orchestra produces beautiful music through the coordinated efforts of its conductor and musicians. Just like an orchestra needs instruments to play music, SPI communication relies on specific lines to transmit data. Let's break down these key components. SCK, serial clock. This is the heartbeat of the SPI communication, the conductor's baton that sets the rhythm. The SCK line carries the clock signal from the master to the slave, synchronizing the data transfer. Imagine a metronome keeping both devices in sync. MOSI, master out, slave in. This is the line where the master sends data to the slave. It's like the conductor giving instructions to a musician. Data travels one bit at a time, synchronized with the SCK signal. MISO, master in, slave out. As the name suggests, this line is for the slave to send data back to the master. It's the musician responding to the conductor's instructions. Data flows in the opposite direction to MOSI, also synchronized with the SCK signal. SS, slave select. In an orchestra, you might have multiple instruments. Similarly, a master device can communicate with multiple slaves. The SS line is used to select which slave the master wants to talk to, like choosing which instrument should play a solo. Each slave device has its own SS line, ensuring only the selected slave participates in the communication. Understanding these components is like reading sheet music. It lets you understand how the SPI protocol orchestrates the flow of data between devices. Now that we know the players and their instruments, let's see the SPI Dance in action. Here's how data is transmitted. 1. Slave selection. The master device first pulls the SS line of the desired slave low, selecting it for communication. It's like tapping a musician on the shoulder, signaling them to get ready. 1. Clock synchronization. The master device then starts sending clock pulses on the SCK line, setting the tempo for the data transfer. The slave device synchronizes itself with this clock signal. It's the rhythmic beat that keeps both devices in sync. 1. Data transmission. With each clock pulse, the master sends a bit of data on the MOSI line and the slave receives it. Simultaneously, the slave can send data back to the master on the MISO line. This synchronized exchange of information is like a perfectly choreographed dance between the master and slave. 1. Data completion. Once the specified number of bits have been transferred, the master stops the clock signal. It then pulls the SS line of the slave high, ending the communication. The dance is complete, and the musician awaits further instructions. This process repeats for every chunk of data that needs to be exchanged. The beauty of SPI lies in its simplicity and efficiency, making it a popular choice for a wide range of applications. Section 5. SPI In Action Real-World Applications. SPI's simplicity and speed make it a popular choice for various applications, from everyday gadgets to complex industrial systems. Here are some real-world examples. SD cards. Remember those tiny cards you use in your camera or smartphone to store photos and videos? They use SPI to communicate with your device, allowing you to quickly store and retrieve large amounts of data. Sensors. Many sensors like temperature sensors, accelerometers, and pressure sensors use SPI to send data back to a microcontroller. This data can then be used to monitor and control various aspects of a system, from the temperature in your refrigerator to the movement of a robot arm. Displays. From the screen on your fitness tracker to the digital display on your microwave, SPI is used to control and update these displays, bringing visual information to life. Communication between microcontrollers. In complex systems, multiple microcontrollers often need to communicate with each other. SPI provides a reliable and efficient way to share data and coordinate tasks between these microcontrollers, much like different departments within a company collaborating on a project. These are just a few examples of the many ways SPI is used in the world around us. Its speed, simplicity, and versatility make it an essential part of countless electronic devices and systems. Section 6. SPI versus the others, comparing communication protocols. SPI is just one of several communication protocols used in embedded systems. Other popular protocols include I2C and UART. Let's see how they compare. I2C, or inter-integrated circuit like SPI, is a synchronous protocol, meaning it uses a clock signal to synchronize data transfer. However, I2C uses only two wires for communication: SDA serial data and SCL serial clock. This makes I2C more suitable for applications where board space is limited. However, I2C is generally slower than SPI. UART, or Universal Asynchronous Receiver Transmitter, unlike SPI and I2C, is an asynchronous protocol, meaning it doesn't rely on a clock signal. Instead, it uses start and stop bits to frame the data. UART is simpler to implement than SPI and I2C, but is also slower and typically used for communication over longer distances. Choosing the right protocol depends on the specific requirements of the application. SPI is a good choice for high-speed, short-distance communication, while I2C is suitable for applications where board space is limited. UART is a good option for simple, long-distance communication. Section 7. Advantages and disadvantages of SPI. Like any other technology, SPI comes with its own set of advantages and disadvantages. Here's a closer look. Advantages: high speed. SPI is significantly faster than I2C and UART, making it suitable for applications requiring high data transfer rates like real-time audio and video streaming. Simple hardware: SPI requires fewer lines and simpler hardware compared to other protocols, making it easier to implement and reducing the overall cost. Full duplex communication. The ability to send and receive data simultaneously makes SPI very efficient for applications requiring two-way communication. Support for multiple slaves. SPI allows a master device to communicate with multiple slave devices, which is beneficial for complex systems with various peripherals. Disadvantages: limited distance. SPI is typically used for short-distance communication due to signal degradation over longer distances. No error checking. SPI lacks built-in error checking mechanisms, which means data corruption can occur without being detected. Increased pin count for multiple slaves. Using multiple slave devices with SPI requires a dedicated SS line for each slave, increasing the total number of pins required on the master device. Despite its limitations, SPI remains a popular choice for its speed, simplicity, and versatility, making it suitable for a wide range of applications. Section 8. Conclusion: SPI's enduring legacy in the digital age. The SPI protocol, with its straightforward design and robust performance, has become a cornerstone of modern electronics. It allows microcontrollers to effortlessly converse with a wide array of peripherals, enabling the creation of sophisticated devices that shape our world. From the smartphones in our pockets to the advanced medical equipment used in hospitals, SPI quietly works behind the scenes, ensuring the seamless flow of data that makes these technologies possible. The beauty of SPI lies in its simplicity and efficiency. Its master-slave architecture, coupled with its synchronized clock signal, allows for high-speed, full-duplex communication with minimal overhead. This makes SPI an ideal choice for applications where speed and reliability are paramount. As technology advances, the need for fast and reliable communication protocols will only grow. SPI, with its proven track record and adaptability, is well positioned to remain a key player in the ever-evolving landscape of embedded systems. Section 9. Looking ahead, SPI's continued relevance. The future of SPI appears bright. Its simplicity, cost-effectiveness, and suitability for a wide range of applications ensure its continued relevance in the digital age. As we enter an era of increasingly interconnected devices, the demand for robust and efficient communication protocols will only intensify, further solidifying SPI's position as a cornerstone of embedded systems design. While newer protocols may emerge, SPI's established presence and widespread adoption guarantee its continued use in various industries for years to come. Its adaptability and compatibility with a wide range of microcontrollers and peripherals make it an attractive choice for both established companies and startups developing cutting-edge technologies. In conclusion, the SPI protocol embodies the essence of elegant engineering, simple yet powerful. It has earned its place as a fundamental building block of modern electronics and will undoubtedly continue to play a vital role in shaping the future of technology.